This presentation provides an introduction to algorithms. Algorithms are a fundamental building block of all computer programs. So what do these things have in common? Doing the laundry, going grocery shopping, and making chocolate chip cookies? Well, each is a repeated action. Every time you have laundry, you have to do it. Every time you need groceries, you have to go to the grocery store. And every time you want fresh, home-baked cookies, you just have to make them. And each of them follows the same steps every time you want to do it. So each of these things can be thought of as an algorithm. An algorithm is just a set of instructions that could be used repeatedly to solve the same problem or task. Why do we use algorithms? Well, once we have an algorithm, we don't have to think about the details of the problem anymore. We already know how to solve it. Once you know how to go to the grocery store, you don't need to whip out the map every time you go. You just go. And all the information we need is in the algorithm. We just have to follow it. And the same algorithm can be used again and again. If it's the right type of algorithm, it can be expanded to solve a bigger problem. And once you have the algorithm, anyone can follow it. So computers have a number of characteristics that make them uniquely suited to solve algorithms. Their speed and accuracy, and the fact that they're well suited to solve tedious problems like searching in a large telephone directory or entering a large column of numbers. Actually, computers are problem-solving machines. So once you develop that technique for solving the problem, once you develop that algorithm, the computer can use the algorithm and solve your problems quickly. But without an algorithm, you don't have a solution. If your algorithm is broad enough, it can solve many different types of problems. So what are the characteristics of a good algorithm? Well, it has to receive input or have initial conditions. And it has to produce a result or an output. All algorithms contain steps that are well ordered, clearly defined, and doable. And there has to be a clear stopping point or condition. And algorithms are general. Well, the good news is you already know about algorithms because you've already used them. One typical algorithm that you've already used is the wiggle, where you ask the turtles to turn right random 90 degrees and turn left random 90 degrees and move forward one. That's an algorithm, and you've used it more than once. There are many different types of algorithms, and you can group them together in ways that highlight how you would apply them to a problem or how the solution could be used. Different ways you might group algorithms include implementation. So if the algorithm is iterative or deterministic, if it has one outcome, or the methodology used, brute force or divide and conquer, for instance, or the application. If you're going to sort a list of numbers or search through a telephone directory, those are different applications. We are going to explore some algorithms based on their types of applications. Some groups of algorithms might be counting, if you need to count a large group of items. Sorting, if you need to sort through a large list of items. Searching, if you need to find an item in a list. Mapping or graphing, perhaps you need to know the shortest distance between 2 points or the cheapest way of getting there. Encryption, either encoding information or decoding information. Packing, how do you make the most items fit in a given space? And mazes, you can use algorithms to create or solve mazes. When you develop an algorithm, you follow the following steps. First, you figure out what the problem is, and then you need to know what the input for that problem is and what you want out of the algorithm. Then you use abstraction and decomposition. You break the problem into its parts and detail all the steps that are required. Then you can write a pseudocode. This is something written not in any particular programming language, but in plain English, that helps you figure out how you're going to write your code. Then you might refine the solution if necessary, and write the code in the programming language that you're using. And of course, you're going to have to debug that code and test the code in different cases to make sure that it works. And then you're done. Let's look at an example. Say you want to take the average of a group of numbers. Well, we know that the input will be a list of numbers, and the output should be the average of that list. And if we want to apply abstraction and decomposition, in other words, if we want to know what the steps are, well, we know that we have to add up the numbers in the list to create a total, when we have to count how many numbers are in the list. And then the average is the total of all the numbers in the list divided by how many numbers are in the list. So the pseudocode for taking the average might look something like this. First, you would initialize the variables total and count to 0. Then for each number in the list, you would add that number to the total variable, and you would add 1 to the count variable. Once you were done with all the numbers in the list, then you would divide the total by count. If we needed to, we could refine the pseudocode, but it seems pretty straightforward. Then we would write it in the programming language that we're using, and then, of course, we would have to debug it. In general, algorithms need to be analyzed. That's because there are many ways to solve the same problem. And when you analyze an algorithm, you evaluate whether or not it's suitable for your problem. Is it fast enough? How much memory does it need? Then you can compare it with other possible algorithms that could be used to solve the same problem. Also, sometimes when you analyze your algorithm, you can find improvements for it. Algorithms tend to become better when they're analyzed. They become shorter, simpler, and more elegant. One technique that's used to analyze algorithms is the big O notation. It's used in computer science, and it's a measure of how your algorithm runs as you increase the amount of data that your algorithm evaluates. So as you increase the input size, you evaluate how much that increases the processing time and the memory used. Big O notation is another way of classifying algorithms. Some common big O values are order n, or order n log n, or n squared. We'll be talking about this in a later video. So in summary, algorithms are a set of instructions that can be used over and over again to solve a particular problem or do a particular task. You use algorithms because you don't have to think about the details of the problem anymore. All the information is contained in the algorithm, and anyone can follow it. Algorithms have the following characteristics. They receive input and produce an output. They contain steps that are well ordered, clearly defined, and doable. Generally, they stop by themselves, or they stop after a certain criterion. And they're general in their application. Algorithm analysis is important because it helps you choose the best algorithm for your task. And one of the methods used is the big O notation. Thank you.